Okay. So today our goal is to make a next step in our, sort of very rapid trajectory through control theory. We will learn what it means to control something. So just to quickly reiterate what we have done so far, we managed to learn how to describe systems that we want to control. We managed to learn what we hope to achieve with the control, namely stability of the system. Now we will finally see what it means to control something, right? So without further ado, let's just go right into it. So let us start by considering two different LTIs, so two different systems that we can work with. Here is one system, x dot equals to x. Here is another system, x dot equals to x plus u, right? So the first one is autonomous. Just to remind you, autonomous means it doesn't have anything except the state, right? In the right-hand side. So x dot depends only on x. Does not depend on u, on t, on anything else. So that is what makes it autonomous. It is autonomous and unstable. So this system is autonomous and unstable, right? Why it is unstable? Well, let's remember the criteria for stability that we learned the last time. Eigenvalues of the system should have non-positive real parts for it to be stable, right? Negative real parts for asymptotic stability, negative for zero for marginal stability. Here, the eigenvalue is 2, all right? For systems of this kind, you could just remember that it's 2. There are all kinds of ways to remember this, but I think it's quite clear, right? And even if you did not know the criterion, you could remember that the solution for this system would be something like x of t equals to initial conditions times exponent of 2 times t, which is a growing exponential function. Depending on the sign of c, it's going to grow upwards or downwards, but towards infinity in either direction, right? So this is unstable. It does not meet our definition of stability, namely solutions that start from different points will all diverge away from each other, right? There's no convergence to one solution. Now let us consider this example. This is a system with a input. So it is not autonomous. There is u. And with that, we cannot say if it is going to be stable or unstable, if the solutions are going to converge to 0 or not, because we don't know what u is. Now, we can decide what u is. We can decide how we pick u if u is control input, right? So let us just assume that u is a control input. So it is something that is within our decision to choose what it is. Now here's the one choice, u equal to 0. If u is equal to 0, then this becomes the equation number 1. Just pick u equal to 0, you get unstable equation number 1. And now we have the answer. Is it stable or unstable? It is unstable for the reasons we discussed previously. But that is not the only choice of u that we can make, right? We can make a choice of u, which would be, for example, u equals to minus 3x. If we substitute here minus 3x, what we get is x dot equals to 2x minus 3x. Yeah, there's a question. Okay, by accident, probably. There's a question, just as I said before, interrupt me anytime, I will answer. All right. So we substitute minus 3x here. What we get is 2x minus 3x, giving us x dot equals to minus x, right? Sure. Okay. And x dot equals to minus x. That is a stable system. Its eigenvalue is -1. So criteria of stability is met. And we know that what the solution is going to be like, right? It's going to be c times exponent of minus t. All right. So we can use control input u to change stability of the system, right? This choice makes it unstable. This choice makes it stable. And in fact, before we chose what control is, it makes very little sense to discuss stability of the system. In this case, it makes sense to discuss stability of this part of the system if we ignore u, right? We could say, could do it. But it does not make sense to discuss stability of the overall system until we chose what u is. That is important part. Okay. Now, let us just get a terminology for what we are going to do this lecture. We're going to work on stabilizing control. And here is the definition. The problem of finding control law U that makes a solution of a system stable, that is called stabilizing control, right? So again, the problem is to find such U that the system becomes stable, right? We're saying here a solution of a system because for nonlinear systems, it will be a particular solution that is stabilized, right? But for linear systems, either a linear system is stable everywhere or it is not stable anywhere. And as I said last lecture, maybe you remember, the only solution that autonomous system with full rank matrix can have is a zero solution. So that's important to remember. Autonomous linear system of the state space form that we have seen in the class. All right. Okay. All right. Now this is very general and might be in general difficult to solve. So let us consider a more particular scenario. And just 1 second, I will pause for a moment. All right. So let us consider problem of linear control, right? So what I'm trying to say here, we're going to consider stabilizing control problem, but when the control has to be linear. So not only the system is linear, but the control is also linear. So let's see it in the example. So here is the classical state space LTI, right? X dot equals to AX plus BU. That's what we have seen on the first lecture, what we have seen on the second lecture, right? Now, the control itself will also be linear, and it would be U equals to minus KX, right? U equals to minus KX. So our game will be to take this guy here and substitute into here, right? So U, that is, could be anything, we will restrict to this form. So what I'm trying to say, in other words, is that U will be a linear function of the state. We could have chosen U in all kinds of ways. U could be a harmonic function. U can be a function of time. U could be some kind of nonlinear function. In general, there is a great variety of U that you can choose. But here we restrict ourselves to making it linear with respect to state. This is going to give us a lot of power in terms of our ability to analyze what is going on. All right. Now, such a matrix K is called control gain. The English word gain basically refers to amplification, right? You can think of it as, something that is amplified 10 times would have a gain of 10. It comes from like radio electronics. Basically, you can think of it as factor by which you multiply something, gain, right? That is the English meaning of the word. Now, this is a control gain matrix. It, as you can see, amplifies X by a factor. Okay. Now, let us see what's going to happen when we apply it. So again, into here, we substitute minus kx. So what you are going to see is minus kx. Here is a minus, right? Used to be a plus here. Now it is a minus because of minus kx. Now notice we have x in front of a and x in front of bk. We can take this x out of the brackets, and it's going to be here. And what is inside the brackets is now a minus bk. This looks like a just a little bit of algebraic operation, and indeed it is. Like, it is very simple. Like, what we did is very simple. But this is fundamental in many ways. This a minus bk, you will see anywhere from your textbook to academic papers published this year. So this is quite fundamental idea, right? Let us observe what we actually have done when we consider this equation. First of all, this equation is autonomous, right? So it is autonomous system. Now it is x dot, which depends on the matrix, times the state, and nothing else. No u, no t, nothing. Only matrix times the state. So it is a linear autonomous system. And for autonomous system, we know how to analyze its stability, all right? So our result from the last lecture, the criterion for stability based on eigenvalues, is directly applicable here. This system has a name. We call it a closed loop system. Closed loop system. Why do we call it closed loop? So the idea, without going into graphical details, there is a sort of way to represent all of this with pictures, and there would actually be a loop, and it's like block diagrams, the representation of control systems. There would actually be a loop which you close, and this is like the motivation. But let me present it to you without pictures, like directly with formulas. So consider u here, right? It is somehow like input to this equation. Now consider x here. It is somehow input to this equation. So equation 4 has input of u. Equation 5 has input of x. Now you can sort of think of it as u goes here, x goes here, right? And you have this like crisscross loop going on, right? X fits here, u fits here, x fits here, u fits here. Now, if we substitute one equation to another, this loop disappears. So it's somehow closed. It all became like one equation. And this whole equation is just this. So that is why we call it a closed loop system, where the controller and the objects themselves are merged into one dynamical system, right? That is all there is to it, to this terminology. Closed loop system. It is good to know those terms like control gain, closed loop system, because they help us to say what we are trying to say in control, right? All of those terminologies are going to be very much useful throughout the course. So I'd recommend you to try to remember them. Okay. All right. Now let us analyze stability of this closed loop system, right? X dot equals to A minus B K times X. Now, as I said before, we can analyze it using eigenvalue analysis. So we take this matrix and we notice that for asymptotic stability, it should have negative real parts of the eigenvalues, right? So this matrix clearly has some eigenvalues. They have real parts, maybe zero real parts, but still, right? So they should be negative for asymptotic stability or non-positive for stability in the sense of Lyapunov, or marginal stability, as they say, right? So negative for asymptotic, marginal for marginal non-positive. Great, great. That is the criterion, right? Now, you can see that saying all of those things about eigenvalues is a little bit cumbersome, right? It's going to be cumbersome. So I will introduce additional terminology, which again is used everywhere. Namely, we'll introduce the idea of a Hurwitz matrix. Hurwitz matrix is such a square matrix M whose eigenvalues have strictly negative real parts. Right? So straight from the definition of stability, matrix whose eigenvalues have strictly negative real parts. Such a matrix will be called Hurwitz. And we can notate it. If we want to notate it very shortly, we just write this. M is in the set of Hurwitz matrices, right? So M is Hurwitz. That's what we're going to say. M is Hurwitz. Now, this stability condition then becomes very simple. It is that A minus BK is Hurwitz. That is the criteria for asymptotic stability. Right. Now, we can formulate the task of finding K. You remember the couple slides ago? We had this definition of stabilizing control, right? One second. Go back. So definition of stabilizing control, right? Here. Now we can formulate it here, and that would go like this. Find such a K that A minus BK is Hurwitz. So find such K that A minus BK is Hurwitz. That would achieve stability of the closed loop system. So the system would become stable. If there is any questions, please ask. If not, then I will move on. Okay. Now we will now go through a few sort of examples, right? I'll go through a few examples. Let us start with a relatively simple example. So scalar case, x dot equals to ax plus bu. All are scalars, right? So we choose linear control law, u equals to minus kx against scalars. So closed loop becomes x dot equal to a minus bk, just a scalar again, times x. Now, as always with scalars, we can just easily solve the equation in this manner. We can say that x of t is equal to x0 times e to the power a minus bkt. Right? Now you can easily notice that this is eigenvalue of the system. For scalar autonomous equations like this, what you always have is eigenvalue goes to the into the exponent is multiplied by t, and here you have initial condition. Right? Okay. Now, as long as a minus bk is negative, the solution is convergent to zero. This is clear from 10, but also from 9, it is clear because of the criteria for stability. So this can be derived either from the criteria or directly from the solution. Now we can pick whichever k we want. So our goal would be to pick such k that a minus bk would be a negative number. For example, minus q, where q is some positive number, right? So let's say q is 10, then we say a minus bk k equal to minus 10. From this, we can just compute k. K in this case would be equal to q plus a divided by b, right? So for example, let me just give you a concrete example. Let's say x dot equals to 5x plus 3u, all right? 5x plus 3u. Now, the a minus bk, in this case, would be 5 minus 3k, right? And that should be Hurwitz, right? We want it to be Hurwitz. Now, what we do is, let's say we want a minus bk to be equal to minus 10. Right? So a minus 5 minus 3k, so a minus bk should be equal to minus 10. Right? Then k would be equal to minus 10 plus 5, all divided by b. So in this case, by 3, divided by 3, which is minus 5 third, right? Is that correct? Let me just carefully double check if I didn't make a mistake somewhere. Right, there is a mistake, no? If you okay, try yeah, of course I made a mistake. Or did I? Yeah, I didn't know. Please sound double check. Did I make a mistake or not? Like in those computations? Tell me.
It probably should be plus 10 and not minus 10 because yeah.
Here? You mean here?
No. In the
Here. Yeah,
formal,
yes,
yeah.
exactly. Good. Yeah, great. So it would be equal to 5, right? Yeah. So, great. Thank you so much. Excellent. And, I knew that there was a mistake, and okay, just sort of like the way I think, I'll share it with you. I'm not sure if this is helpful or not. K, in this case, you should expect it to be positive. Why do I expect it to be positive? Because the control law already has this minus sign, right? The control law usually tries to punish positive x by associating it with negative u. All right. So k should be positive. That's what we would expect normally, unless of course I asked for such a q which would be smaller than a. So let's say a was already let's say minus 20, and I asked for q which would be 10, then k could be like negative, right? We don't have to go into this, but if you want after the class, just try to figure out what would happen if your a is like minus 20 and your closed loop matrix would have eigenvalue of like minus 10. How does k behave in this way, in this case? Right. But yeah, so that's why I was surprised that with my original result. But yeah, good, 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 good. Thank you again. All right. And with that, we get a, if we substitute, okay, let me get it back. If we substitute this k into here, what we get is, oh, let me just edit it. We get here minus 5 x, right? Which is the same as 5 minus 15 x, which is the same as minus 10x. And you can see we achieved exactly what we wanted. So this guy here, minus 10, that's exactly what we have here. That's eigenvalue of the closed loop system. Okay, so relatively easy in this example, right? We can just make a formula how to compute k given eigenvalue of the closed loop system that we want. Let us consider a more complicated example. So here I present you a 2x2 system, right? So system with two states. The state space of the system is two-dimensional, x1, x2. The state matrix is like this, is the upper triangular, right? Here's a control matrix, B. It has a B, small b here, 0 here. The control law is linear, and let us notice that this is how it is written, right? This is how it's written. Why is it not a matrix? Can someone tell me? Why is it not a matrix? Why? Oh, sorry, it is a matrix, of course. But I'm saying is, why it is not 2x2? It is 1x2. Why is it not 2x2?
Maybe so we can multiply them.
Maybe so we can multiply them.
Like this B0 vector.
Mhm, mhm. Yeah, so dimensionality, right? So the question is about dimensionality, right?
Yeah.
1 second. Let me go back to presentation. Wait, just a moment. Okay, sorry about that. Yeah, exactly. So it is about dimensionality. And how we can see it is that here, this B matrix would take a scalar as an input, so one-dimensional U. So U has to be one-dimensional. So the output of this K matrix would be one-dimensional. The input of this matrix is two-dimensional, so it has to be 1/2. And in general, this is very easy to do in all LTI systems. Like you want to understand what K matrix is in shape, you know that it has to, like the output of the K matrix would be the same as input of B matrix. The input of K matrix would be the state. So the same as, for example, input and output of the state matrix. It's quite simple to analyze. All right, good. So our task now is to find K1 and K2 such that the system will be stable. Now, let us look into what happens if we substitute this guy into here, right? What happens? What happens is, so first of all, like this guy here, when multiplied by U, would become, I'll just write it here somewhere, will become B times K1 X1 plus K2 X2. right? That's what is going to happen here. All right. Now, our goal would be to rewrite this expression here in such a way that it is something multiplied by x, right? Because we want to like find this closed loop matrix, matrix. So the bottom of the matrix is going to be zeros, right? That's what we know. The top of the matrix is going to be something like this. I'll just write here. Will be b times k1. That is what's going to be multiplied by x1, right? It's going to be k2. That's what's going to be multiplied by x2. And here is 0, and here is 0, right? So that is what we are going to have. And that is like the matrix, right? And the vector here is basically x1, x2, right? That's what's going, what I represented here is basically this, right? Those two are the same thing. Now, I did it by first multiplying the b times u, where u was like this guy multiplied, and then kind of like trying to rewrite it in terms of this whole, matrix vector multiplication. Hopefully it was clear, right? Like relatively clear. But it's not the cleanest way to do it. I think the advantage of doing it this way is that at least you feel like you are grounded, like you feel like you are not going into any sort of strange abstract linear algebra. But the more reasonable way to do it goes like this. So this is a B matrix, right? This is a B matrix. This is a K matrix. Okay? So basically, all you want to do is to just multiply B times K, right? B times K. That is what you want to do. That is all you want. Now, how do you multiply a 2 by 1 matrix with a 1 by 2 vector? Oh, sorry, 2 by 1 matrix with a 1 by 2 matrix, right? How do you multiply them? Well, very simple. You just check if they can be multiplied, and then you multiply them. Can they be multiplied? Well, for the two matrices to be multiplied, the second dimension of the first one has to agree with the first dimension of the second one. And indeed they agree, 1, 1. So the multiplication would go something like this. First element of this matrix, right? So the second matrix times first element of this matrix. That's what goes here. Next, what you do is, let me be careful. Second element of this matrix, of the first matrix, times first first column of this matrix, right? So we will go in row by row here. Here we go column by column. So second row of this matrix times first column of this matrix. All right, that is this element. Okay, 0 times k1 is 0. Next, you go first row of this matrix times second column of this matrix. That is how you get this guy. Finally, second row of this matrix times second column of this matrix. That's how you get this guy, right? If you're familiar with this, it looks very much like auto product. But in the end of the day, this is just matrix multiplication. Just because they look kind of like strange, because they are like, they kind of resemble vectors, but they try to multiply along a wrong dimension, it doesn't mean that there is a problem. Indeed, there is no problem. it is perfectly natural operation to multiply this type of matrix by this type of matrix, and that is the result. Visually, it resembles auto product. Indeed, in some sense, it is exactly that. It is the auto product, right? But
It also looks like if we multiply scalar b by the vector k, and we just get it scaled by b,
yeah,
and
indeed,
also additional row.
yep, indeed, this is true. This is true. But overall, even there was no zero here, there was something else, would still hold. It would be still just as easy. You multiply, like you know how to multiply two matrices, even if they are one by something or something by one. You know, there's a one of the like there's only one column or one row. Go ahead and do it. Don't invent new rules for matrix multiplication just because the matrix looks strange. Right? Okay, good. So the result would be this guy. Okay, let me get this back. So the result would be this guy. A11 from here minus BK1, right? This from here. Minus is this minus, right? A12 from here plus this guy, again minus from here. Right? So it is A11 minus BK1, A12 minus BK2. This zero is a combination of this zero and this zero, right? And A22 is a combination of A22 and this zero. Okay. So this is now the matrix that represents the closed loop system, right? This is a closed loop system matrix. Remember last lecture, I told you a criterion for how to find eigenvalues of an upper diagonal matrix. Well, here's the opportunity to use it, right? Can someone tell me what is the eigenvalues of upper diagonal matrix are?
Just elements from diagonal.
Exactly. Yeah, very good. So it is, this is one eigenvalue, this is another eigenvalue. Now, we can see that this eigenvalue, we can make whatever we want, same as before, right? So we, whatever we want, we can make it. Just choose Q, which is a positive number. Q would be, minus Q would be your eigenvalue. Choose K1 in such a way that, K1 is equal to Q plus A11 divided by B. Okay, good. But we cannot do anything about the second eigenvalue. Second eigenvalue is out of our control, right? So if A22 is already negative, then we can stabilize this system. So we can make the system stable. But if A22 is not stable, if not negative, we have no options. We cannot do anything. So here we rely on A22 being negative without us doing anything. That's quite interesting. Okay, so what we have seen so far is called pole placement. That is a method where you find K in such a way that your eigenvalues, which we, for various reasons, call sometimes poles, that is older terminology in control theory. So your poles assume the values that you want, right? So that is the pole placement method. You can see it is a little bit laborious, but it can be done. But you can do it automatically too. For example, in MATLAB, you just write it like this. K is equal to place A, B, and P, where P are your desired eigenvalues. All right? That's it. Next. We can do control not only on for stabilization, but also for trajectory tracking. which is essentially going to be the same thing, but with a change of variables. Let me demonstrate. So let's say that x star and u star represent a solution to the equation x dot equals to ax plus bu, right? What does it mean to be a solution? It means that x dot star is equal to ax star plus bu star, right? So we substitute them into the equation, we get a equality. So we call such x star a reference or reference input, right? And u is called feed-forward control, right? So those are the names. So reference as in like what you try to follow, and feed-forward control as opposed to feedback control, which is minus kx, right? If for now you can just remember it's called feed-forward. Later, maybe we'll discuss a little bit more why feed-forward, feedback, why those terms. Okay. Now, what we do is we find the difference between x, this equation, x dot equals to ax plus bu, and this equation, x dot star equals to ax star plus bu star. So the difference is going to be a star minus x dot, ax star dot minus x dot is equal to a times x star minus x plus b times u star minus u, right? So we just put a out of the brackets and b out of the brackets, and that's what we get, right? Now I introduce new variables. So this x star minus x is now going to be called e as an error, e. Okay? And this guy, u star minus u, is going to be called v, right? And in terms of new variables, this equation 31 becomes just this. Is e dot equals to ae plus bv. And you can see this is just the same LTI as we have been used to, right? So with that transformation, we can simply pose the question how to find the stabilizing control error for this equation. This equation itself is called error dynamics. This E is called control error. We find our stabilizing control in the same form as before. V is equal to minus KE, in terms of new variables. We substitute, we get E dot equals to A minus BKE, right? So same process. And we find such K that it is stable. That's it. Now, when we go to original variables, what's going to happen is that this E, it was like x star minus x, right? So it's going to be x star minus x in the original variables. And this V, it was u star, it was u star minus u, right? So you put u to the right-hand side. Let me just make sure that I don't say anything wrong. It should be u star minus u, right? U star minus u. Yeah. So you put you multiply it by -1, put u star to the right-hand side. That's how you get rid of this minus here. This minus disappears, right? Because you multiply by -1, and you get this additional term here. Now, this form is what we call like control, right? This is what we would call feedback control. This is what we would call feed-forward control, right? Okay. Now, what I showed you was a little bit fast. If you want, next time we can just go through it slower. But at the end of the day, this is what you do with trajectory tracking in linear control. You simply introduce a reference in this form, new variables. You stabilize exact same system that you would have stabilized for any control task. You can see there is no difference between trajectory tracking and stabilizing the origin in linear control. In both cases, you simply find such k that a minus bk is stable. And that's it. The control law would be slightly different though. It will be those two new terms, which would exactly allow you to track your trajectory. If there was no x star in u, you would state the origin, right? But with them, you track a trajectory. So that's it. That's it in terms of trajectory tracking. All right. I will leave a couple more next slides for the next lecture. We'll begin with them because I think we are out of time. Am I correct? Right? Sound, please tell me.
We actually have 10 minutes.
10 minutes. We have 10 minutes. Okay, good. That will be enough for the rest of the slide. Okay, I didn't compute the duration of the lecture correctly. Okay, that makes me happy. Let us finish the lecture today then. Now, what we did here was the trajectory tracking, right? Maybe since we have 10 minutes, let me explain a little bit more about what trajectory tracking looks like visually, right? So let's say you have your, okay, well, let me just do it in terms of colors. Let's say we have our state space, right? We have the origin here, right? So a control that stabilizes the origin basically tries to make sure that your trajectory goes like your trajectory of your state goes towards the origin. That is what stabilizing control does. Now, if you have a trajectory tracking, you may have a reference trajectory that goes maybe something like this, right? That is maybe your reference trajectory. And then if you have such a reference trajectory, then your actual what your goal is for your actual trajectory to approach this trajectory asymptotically, and sort of visually it would kind of like merge into it, right? So that is the idea of trajectory tracking. If you can imagine, most cases in control are trajectory tracking cases. Your airplane, when it tries to fly from one city to another, tracks a trajectory. Your car, when it tries to change lanes, tracks a trajectory. I'm simplifying a little bit, but you get the idea, right? Like your, photo shoot drone, when it tries to, go around you to make like those photos or videos, it tracks a trajectory. But as I just demonstrated, this is, in terms of linear control, equivalent to stabilizing origin. So those two problems seems to be equivalent. Now, sometimes a trajectory would not have would look like this, right? There's just ax star plus bu star without any derivative here. Basically, this means that this is not really a trajectory. This is just a point, which is not the origin, right? This is just a point somewhere else in the state space where we want to sit. So you can imagine you have a manipulator which sits in a particular pose. It doesn't sit in a pose where all joints are equal to 0, right? Maybe this pose. It sits in some particular pose. Joints are not in 0 positions. They are somewhere, right? So you can think of it as the desired position of your joints, and this as, for example, gravity compensation, okay? From mathematical point of view, this is only different from the previous case because of this 0, right? Now we can repeat exact same process and we will be done, right? We don't need to invent anything else. And in fact, that is exactly what we are going to do. The only interesting part about this special case is that we don't really need to know u star because we can compute it. And we can compute it simply by solving equation 35 using least squares. So basically, we can put a x star to the right-hand side with a minus. And then we get b u star equals to minus a x star. And this guy, if we pseudo-invert it, that is pseudo-inverse, or in other words, if we solve least square problem, so we find the least residual solution for this equation, we get this. So if you want to stabilize a particular point in the state space, not origin, what you need to do is to just consider this problem and make sure that there exists such u star that makes equation 35 into equality. That is all. So, as I said, trajectory is equivalent to stabilizing the origin. Stabilizing arbitrary point in state space is equivalent to stabilizing the origin, provided that you can find such trajectory, or provided that you can find such u star that turns 35 into equality. All right? So in practice, of course, like this is again one of those practical problems that you would probably be solving if you're doing control. All right. I think in terms of okay, last bit. Let me just double check. Yeah, we still have time. So we could do one more thing. And that is to sort of like change the system into a system with new input, right? The system with new input. So consider this old system. The input here was u, right? We do trajectory tracking control on it. We get u equals to k minus x star minus x, k times x star minus x plus u star. We substitute here, right? So after substitution, here's what we get. We multiply u by b, we get b k x minus x star plus b u star, right? We group terms, we get this new control matrix. We get this guy times x star, this guy times u star. Now, for simplicity, let me just assume that u star is equal to 0. I'm here. I'm like just making a huge assumption. Just to make a point. Of course, like in practice, it's not going to be 0 for almost any reasonable trajectory. Okay, but let's just assume it is 0. What we have is new state matrix, but also new input. Like this is new B matrix, and this is your new input. So in a way, you can think of applying control as changing not only the state matrix, but also the input. Now, in some sense, your reference is your new input. And this you can look as some strange mathematical trick which makes no real impression on reality, but that's not so. If you have seen server controller or servo motor, or if you have seen a motor which is controlled by sending to it angles instead of voltages, that is what you are seeing, right? You have already a closed loop control inside your servo motor, or inside your, let's say, KUKA manipulator motor, which controls one of the joints of the robot arm. They are not allowing you to send them voltages. They already abstract this away from you. Their input would be desired angles, but those are still inputs, and you can still think of this whole system as a system with an input. And that is basically the idea how you would do it. Of course, again, I made this assumption just to make it short and clean. But in practice, you don't make assumptions about what you are dealing with. You have to sort of control what you get. But yeah, that is how you can change input. So your input is not always the same as what your physical system sort of like implies. It depends also on layers of control. Okay, now I want to quickly show you something. I think at this point, maybe we need like sort of like some kind of map. And isn't the experiment. So if it doesn't work, I apologize, but maybe hopefully it would work for some of you. I want to just show you where we are, and I will try to keep this keep track of this progress as we go through the course. So far, we have seen two representations of what we are going to control, right? ODE and state space. That was the first lecture, right? In the first lecture, we also saw single input, single output, multiple input, multi-output systems. This we don't know yet why we learned this. We will understand this next lecture. But for this lecture, so far, we just know that they exist. But we are already very much do know why we learned those two representations. Notice that this representation, state space, allows us to do Lyapunov stability analysis using eigenvalues, right? And any system can be represented in state space. So for any system, we can do Lyapunov stability analysis. That is our key idea, right? For ODE, on the other hand, we can do this very nice trick for second-order systems. So ODE also gives us a little bit of benefit. For second-order system, like spring pass damper, much easier to analyze stability looking at the coefficients than trying to look at eigenvalues. So there is a benefit on both sides. And also ODE is how we get our models from physics. State space is where is to what we converted. So in many ways, you can see it as like we get model here, convert it here, go to for stability analysis here, right? And now this lecture, we also learned how to, so like this is why, right, Lyapunov stability. Now this lecture, we learned how to make something stable using what we call static feedback. What we learned today is a static feedback, as opposed to other things that we will learn later in the course, right? So we now know how. And this static feedback, we know how to do it, like by analyzing eigenvalues. But if we are going to do it automatically using, let's say, place operator in MATLAB, we're going to require state space, right? So there is this direct connection to state space again, because the toolbox requires state space representation. So I hope you kind of get the idea why we started with state space and ODE, went to stability, went to static feedback, right? Like stability motivates why we need to control anything. But in the labs, for example, that you are going to do in your practical sessions, you are going to use state space representation specifically for both for stability, Lyapunov stability design check, and for stabilizing control design. So those are all interconnected, they're all interlinked. And as we go on, we would have more of those. Right, I think that is it for this lecture. And if you have questions, I will stop the recording and we can answer if you have any questions.